Hi, I'm Tong from ION in China. This is a brief introduction to the project using the microstimulation to investigate the role of motor cortex in macaque monkey. To understand movement is not easy, especially the motor preparation. It has always been a mystery. This process is time-consuming, so longer the delay period, shorter the reaction times. Neural preparatory activities in the motor cortex, especially the dorsal premotor cortex, are heterogeneous. Are these neural activities important? To verify their roles, causal evidence are needed. Intracortical microstimulation ICMS is a classic intervention tool. In motor cortex, subthreshold ICMS has been used to evoke or disrupt voluntary movements. In a study in 2007, short-chain subthreshold ICMS are delivered to PMd or M1 during the delay period of the center-out task. ICMS in PMd around GoQ specifically prolonged RT, which supported the optimal subspace hypothesis that movement preparation is an optimizing process, that movement will be delayed until errors are eliminated. However, very recently, a study used almost the same experimental setup found that stimulation in PMD either significantly shortened RT or induced no effect, regardless of the inconsistency. Whether the change of RT could support the hypothesis is worth discussing. Reaction time actually consists of at least three components. With a fixed position target, it is hard to tell which component is affected by ICMS, but it is possible in the interception task with moving target. Let's leave out the attention for the moment. There can be three potential results. First, if ICMS distracts motor planning, the prolonged RT should be the same to center out, but the time cost to replan the movement are similar. Second, if movement initiation is disrupted, same RT, but as the motor plan is intact, subject reaches to the left position and makes an error. Third, if the brain guarantees a correct reach at all costs, as long as the error could happen, extra time will be taken to form new motor planning, and RT should be longer than the center out. To examine these possibilities, we deliver the microstimulation to motor cortex when monkey is doing the manual delay interception task. The stimulation randomly expands the whole delay period. We focus on those results of stimulation around goal signal. We first examine the effect in M1. As you can see, stimulation increased RT in both center-out and interception tasks, and the increment of RT is larger in interception. We also found that after stimulation, movement time MT reduced, and the percentage of RT increased in interception. Stimulation caused a minimal impact on the endpoint and the velocity of movement trajectory. Thus, so far, the results seem to support the third possibility. However, as we continue the stimulation experiments, the ICMS effect changed. Except in the first 8 sessions that RT is prolonged, in the rest of M1 sessions and the PMD sessions started later, ICMS induced significantly shorter RT. Besides, we found a sharp decrease of RT after this time point, which may be caused by the high amplitude of stimulating current. As you may remember, both ICMS effects have been interpreted as intervention, and they appeared at the same time in our study. How come? As the changing profile of a reaction time is reminiscent of an adaptation or learning process, some explicit signal may be involved. Can monkey sense microstimulation in motor cortex? To answer this question, we trained the monkey to do the visual goal replace task. We decreased the visibility of visual goal cue block by block, while in the stimulated trials, subthreshold stimulation is delivered exactly at goal. To encourage the monkey to follow the ICMS goal cue, we also adjusted the amount of liquid reward with RT. As expected, after training, the monkey learned to use the stimulation as goal cue. In the example block in M1, when goal cue is still visible, both ST and NS trials followed goal cue. For the slope of the regression of delay duration versus delay plus RT are positive. When goal is invisible, the slope of NS trials decreased, suggests more random movement onset time, while the slope of ST trials maintained. The results are similar in PMD. As control, in primary somatosensory cortex associated with arm, we even found the stimulating intensity-dependent effect that stimulating current amplitude correlated with the slope of ST trials. To summarize, we observed an adaptive kinematics change after continuous microstimulation in motor cortex, which may be caused by both perturbation and perception. This suggests that for the new generation of bidirectional BNI, decoding and feedback could be realized by solely one electrode array in motor cortex with less trauma and less cost. Thank you, and further discussions are welcomed.